All right. So we talked about linked list, great. We talked about, let's see, iterating through it, beautiful. We talked, traversing it. We talked about the code, we wrote the code. We talked about insertion, where we had a previous and a next. They call it P, that's great. And hey, look, they have a really complicated pictorial representation. Hey, let's go over this real quick, just make sure we're all on the same page. 45, 65, 35, 76, and what are we adding? I don't know. A new node after 65, it looks like. So we created a node after 65, new node points there, and then, oh yeah, we didn't do insert. Oh, that's what we didn't do.
Yeah, 'cause we added the back and added the front, but not
in the middle. Oh yeah. Thinking maybe I'll leave that as an exercise, because that will be in your lab. Gotta at least give you something. So we didn't do that one, so we'll think about that one. All right, we talked about insertion, right? So got to create a pointer to the next and update it. But we did this with remove. Actually, I think remove is way more complicated than insertion. Hopefully, but I could be wrong. Hey, deletion. They call it remove. If it's in the middle, you go across it. Perfect. So, right, so you had to keep it temporary. Beautiful. Great, that's what we did. Whoops. Building a linked list forward and backwards, we did that with push front and push back. We had a first, last, perfect. Just running through these slides. And structure of the node. Wow, they really talked, oh, we're not doing iterators because that's silly. Destroying the list. Oh, we didn't destroy the list. We started to. So you do need to have a destructor. And you just need to go through deleting each one. There are easy ways and hard ways to do this. I'm going to show you a trick because I believe it is vitally important that you learn this trick. Because you should never code more than you have to. So, we could do the whole traverse through the entire linked list, deleting every element one at a time. Or we could just do while mhead does not equal null, remove mhead.get data. AKA, well, the head's not null, remove it until it's not null anymore. The reason why I highly suggest you use this type of trick, one, it's easier to code. Two, it is less error prone because now you only have one function that actually does deleting, aka remove, as opposed to having a remove function and a deconstructor function that are trying to call remove and are going to mess you up. Now, technically someone can argue that this is slower than writing a custom function to remove it all. Yes, I agree, but you're just trying to pass this class. So I highly recommend you do it this way. Also in the real world, you want to write your code, it's more important to write it correctly, and then if there are performance problems, fix it later. I know most of the time you want to write it correctly the first time, but this is one of the situations where, trust me, do it the easy way, the more correct way, that's not going to cause you errors, and then you can fix performance later. All right, let's make sure that doesn't blow up in our face. Has no member get data, probably because it was called get val. Boom. All right. All right, so that was the destructor, initialize, print, length. Oh, we didn't talk about the length. Ooh, yeah, now that's definitely something y'all are going to do. What are some options with the length of a linked list? Yes?
For the deconstructor, would you also want to just delete the entire SLL, or would you just want to delete everything in it?
So with the deconstructor, what's happening inside the compiler, the short answer is delete everything in it. And the reason for that is the deconstructor is called when the entire object is going to be deleted. So the C++ runtime is about ready to remove the object, and it's asking you, please remove everything inside it first before I remove you altogether. Good question. So length, what can we do about length?
So like how many objects are in the list?
Yes, how many elements are in the list? Or SL nodes are in the list, sure.
You can't keep track of it like throughout your functions.
Right, so you could create an M size, and every time you add something successfully, increment it by 1. Every time you remove something successfully, decrement it by 1. Sure. Or you could traverse the whole linked list, adding 1 to a variable and then return that. Sure. Which one's better?
It depends.
There you go. So keeping the variable, it's definitely, it makes get length an O of 1 operation, which is good. But it does add another variable to your data structure, which makes it slightly bigger. Although that's not much, it's 4 bytes, who really cares? But in some situations that may matter. I recommend doing the variable way. And I'll let y'all do that. Retrieving the data first and last, that's nice. Beginning and end, copying the list. Ooh, yeah, you gotta copy the list over. Again, I highly recommend you do that the easy way. As you iterate through one list, push it to call push back. Don't try and create the nodes, just use the function you already created to help you. That way, if there's an error, you only have to fix it in one function as opposed to like 5 functions or something. All right, deconstructor, great. Overloading, we're not going to talk about that. Unload linked list. All right, we're done with these slides. Oh yeah, any questions about linked list before I go to the lab?